All right, example 8, still going on this related rate stuff. A conical tank with the vertex down, so the pointy part is down, is 10 feet across at the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. Okay, so we have a cone. And we're assuming it's a right cone. It's not like tilted over to one side. I would not give you a problem like that, just FYI. Physics might, but not in here. Okay, so there's your tank. So we know that it's 10 feet across the whole entire top. So that would be the diameter, which means the radius is 5. And then the height, or the entire depth of the tank, is 12. So the tank is filling up with water, so the water level is rising, and then the radius of the surface of the water is also increasing. All right, so we've got like a height of that little green triangle and a radius, or the little base of the green triangle. Okay, so let's come back to the drawing in just a second. So let's list out what we know, what we're given, and what we need to find. Okay, so the know. They gave us a rate here of 10 cubic feet per minute. Well, cubic feet, anytime it's a cubic something or other, that's talking about a volume. So it wants us to kind of work with the volume of the cone. So 1/3 pi r squared h. And what are we given? So it's the water's flowing into the tank at a rate of 10 cubic feet per minute. So we know the dVdt is 10. And we want it specifically when the depth or the height of the water is 8. And then the find the rate of change of the depth or the height. So find dH/dt. So I am going to have to take the derivative of this volume equation, but this is one of those examples where it's in terms of more than one variable. The volume is in terms of r and h, which means that if I go through and find the derivative of this, I'm going to have to use the product rule, but I'm also going to have a dr dt show up, and they didn't say anything about it. So instead of leaving it in terms of r and h, let's try to get the volume in terms of just a single variable, either in terms of r or in terms of h. And we'll talk about how to decide between the two in just a second. So first of all, let's get a relationship going between r and h. So that's why in this little diagram over here, I drew this little triangle, because you have the big triangle, the big right triangle, and the little one. These are similar triangles. So you can set up a ratio between the two, and there's lots of ways you can set it up. The key for it is to just be consistent. So what I do is I take just the same, or just the size of the big triangle, so 5 and the 12, and then I take the two sides of the small triangle in the same order, and just write them out here. So the small one on top was r, the one up and down is h, and there's your ratio. And then just cross multiply. So 12r is equal to 5h. And you can solve for either the r or solve for the h. Well, we want to be smart about which one we solve for. We want to find dH dt. So that means in my volume equation, I need h's. I do not want r's. So r is what has to substitute out. So I'm going to solve for r and get 5/12 h. So that's what's going to plug into the r. And then I'm going to simplify this just a little bit. I'm going to keep the 1/3 pi kind of separate. But I'm going to square this stuff in here. So it's 25 over 144. And then that's h squared times h would be h to the third. So now that it's in terms of just h, now I'm going to take a derivative. So the 3 is going to pull down and it's going to cancel off the 1/3. The 25 stays where it is, as well as the 144 times h squared dh dt. Okay, so now I can plug in all my givens. So the 10 goes in for the dv dt. Let's rewrite that fraction a little bit nicer. The h is 8. And dh dt is what I'm trying to find. So now I can find it. So just swing all this stuff over to the 10. And once you simplify it down, it's 9 over 10 pi. And then the units would be feet per minute because it's talking about the rate of change of the height. Height is just a single length. And there is your dh dt. Okay, so these related rate problems, this is about as tough as they're gonna get. Because this one is a little bit tricky because you're having to deal with 2 different variables in there. So this is a way to fix it so that it's only in terms of h. So if they wanted to know the dr dt, then I would have solved this equation here for the h. So it just depends on what they want you to find, and that'll tell you what variable you want to keep in your equation. So if you're finding dh dt, you want to keep the h and get rid of r. If you want the dr dt, you're keeping the r's and you got to get rid of the h. So just kind of pay attention to what they're asking, what they want you to find. All right, last example. Circle is inscribed in a square. So the circle is inside the square. The circumference of the circle is increasing at a constant rate of 6 inches per second. As the circle expands, the square expands to maintain the condition of tangency. Find the rate at which the perimeter of the square is increasing. Okay, so here's our square. And we've got a circle on the inside. So the circle has a radius which means the side of the square is going to be the whole diameter. So the side of the square is going to be 2r. Okay, so what do we actually know? Well, they talked about the circumference, so that better be 1. The circumference of a circle is just 2 pi r. What are we given? Well, we know that the circumference is increasing at a constant rate of 6. So dc dt is equal to 6. Okay, so they want us to find the rate at which the perimeter is changing. So dp dt. Well, I have no variable of p in my no equation, so I gotta get one in there. I don't want anything about r, so let's kind of use this shape, this geometric shape, to kind of relate the radius of the r to the perimeter. So the perimeter of the square would be 8r, which means r would equal p over 8. So I can substitute the p over 8 in for r. And simplify it down. So pi times p all over 4. And now I can take a derivative because it's in terms of the variable I wanted. So dc dt equals the pi over 4 times dp dt. The dc dt is 6. So just multiply both sides by 4 over pi. And we get 24 over pi. And the perimeter, it's still a length. So it's still a length, so its units are going to be inches per second. dp dt. Okay, so that is going to do it for section 3.7 as well as the chapter. So make sure you are trying the homework problems with these because you're going to want to. And just give it a shot. So don't be discouraged if you're like, oh my gosh, these problems are kind of hard. They are hard. They are tough. Every calculus student thinks that they're tough. But they are necessary because you're going to see them a lot when you get into physics and chemistry and the applied sciences. So give them a shot. It's normal to struggle a little bit. Don't think you're stupid or anything. You guys can all do this. You got into calculus for a reason because you're smart. So don't let these problems defeat you. So try them out. Let me know what your questions are and I'll help you as best as I can. Okay.